Hi, everyone. I'm Varun. I'm a research scientist at WhatsApp. And this talk is about WhatsApp's private processing. And this is a very technical talk, engineering talk. And I'm just going to kick off with a bit of a recap and some of the products that we're actually working on that we've launched in the last couple of years. But otherwise, this talk is mostly going to be about how we actually build this platform, and more importantly, about our experience running an actual production service on Tees for over a year, which is a AI production service at scale. And so first of all, just a quick recap on what we've been doing at Meta with private processing. We started off in 2022 with SGX, and we just used SGX for some signing keys at the edge. Then we moved to AMD CVMs for some internal services in 2024, and we created the remote attestation TLS protocol for our services. In 2025, we launched our first products on the WhatsApp private processing platform, first user-facing products. And in 2026, we're continuing to build on that and launching newer products, which I will talk about shortly. So what is our goal? At WhatsApp, we're trying to get AI to everyone in a way that's completely private, in a way that is essentially the same as what WhatsApp's messaging is, end-to-end encrypted. When you send a message to someone else, they cannot see, no one can see what you send them except the recipient of the message. Similarly, with WhatsApp's private processing, whatever you send to the AI cannot be seen by anyone except the AI model itself. And not even Meta or WhatsApp can actually see what you're interacting with the AI about. And this is built in an open, verifiable way, which is actually audited by security experts. And in parallel, we're also heavily investing in actually making parts of these open source, and so that anyone can actually build these things and verify what the T is doing with their personal data. And so quickly, two of the products that we launched in 2025, summarization. You have long chats that you cannot catch up on. You can quickly summarize them with AI, which is summarized in a T, so nobody can see it except you. Write with AI, get some writing help on rephrasing things and things like that inside WhatsApp. And more recently, last month, we actually launched Incognito Chat with Meta AI, which is now our flagship product of private processing in WhatsApp. Essentially, it's a chat with Meta AI that you can, it just works like the normal chat with Meta AI, but completely runs within Ts that you can talk to without Meta being able to see your messages. And when you close it, everything kind of disappears. So it's fully ephemeral. That's why incognito. So now Kevin will talk about how we actually built it, overview of the platform. Kevin? Yep.
Hi. Sorry, guys. We're going to be doing this weird baton pass first, so please forgive us. I'm Kevin. I'm part of the infra team that helped build out like a lot of the infrastructure that powers private processing. Let's just do like a very quick overview of like what private processing looks like, and give you an intuition so you can kind of understand the rest of the slides. We have a WhatsApp client who wants to go talk to like a lot of like the Ts that are running inside of our private processing stack. We have two major stacks, Ts here. We have the orchestrator and a predictor. The orchestrator is effectively just the front end that will just route all of the inference requests over to these predictors, which are have the GPU cards attached. They're just NVIDIA Hopper GPUs, and they are running in the CC mode. We also have a load balancer, which just standard fare. You're just going to send it to an orchestrator. We have an anonymous credential service, which is what we're going to be using in order to kind of like authenticate your app, your WhatsApp clients, while we're trying to anonymize them and prevent them from being targeted or something like that. There's also just the standard WhatsApp server, which is how you're going to be getting your responses. Here, the orchestrator is going to be doing a lot of remote attestation with all of the predictors, so that the orchestrator knows that it's talking to legitimate predictors. And the client is going to be talking, or is going to connect to the private processing stack through a oblivious HTTP relay, which will help hide your IP from Meta, so we can't do any sort of like targeted attack against you. We also have transparency logs that are coming from Cloudflare. This contains all of the transparency proofs, which represent all of the measurements in the trusted computing base for all of the orchestrator and predictor jobs. These are stored inside the orchestrators themselves and the predictors, so that we can bundle them as part of the attestation report. And then the client will go and talk to the anonymous credential service, get some sort of token that will be used to authenticate within the meta infrastructure, and we can kind of use the oblivious HTTP relay to go and authenticate with the orchestrator and kind of do all of that. Afterwards, the orchestrator will take the it'll take any sort of requests or any user prompts that are coming from the WhatsApp client, pass it over to the predictor. Predictor will do some inference and then return the results of that through the WhatsApp server and back to the client. All right, so that's just a very quick overview of the actual platform itself. Let's talk a little bit about some of the features we saw and some of the challenges that we encountered when we were developing private processing. So one of the things that we initially started off doing was we would build all of the image alongside of the application. So we would tell developers, hey, go build all of your VM images and then or rather build all of your applications and then install it into this VM image, and then it would cause this whole dependency issue where you would have to build and rebuild. Yeah, you have to rebuild the entire world and just kind of do this weird dance where you just build everything. It would cause builds to take 30 minutes and just add all these dependency issues. So we had to think about how we would actually separate some of the builds, kind of dependencies and all of these T related concepts, such that we can kind of own parts of it, and then kind of the service owners, so WhatsApp and other people can kind of focus on their own business logic. So we think of it as this generic abstraction on top of the applications that service owners will use. So here we've separated into two interfaces here. We have the application agnostic CVM. Internally, we call it the generic CVM. And this is where we abstract all of the T integrations. We provide all of our platform daemons here, and then we also use this to launch the application container. The application container I can show you here is effectively just what the service owner is going to provide to us, and also a bunch of the application containers and data components. And then if you see in the rest of the diagram here, in blue, that's everything we own, and then AMD firmware is also provided there as well. So how do we add these application containers into the CVM, but also can securely ingest those such that they're part of our trusted computing base? This is something else that we also thought was going to be an interesting issue. I'm sure there are a bunch of open source solutions, but this is how we did it at Meta. So the issue with our initial idea of having these generic CVMs is that this base CVM can only serve multiple. It can serve multiple services, but it's not part of that trusted computing base. Recall that we're going to be separating all of these together. We're going to be separating all of these application containers from the actual image. So if we were to try to do any sort of attestation, they wouldn't be included. But so we had to come up with some sort of artifact injection framework such that we can ingest the untrusted data, such as the application data or model prompts or whatever, and then kind of verify them through this TSA model. I just hope that this implementation is a little bit more secure than the TSA. But anyways, the idea here is that we want to have this dedicated channel where we are guaranteed that we can ensure that all of the untrusted data comes through this particular channel and through no other method, such as a shared file system or anything like that. This allows us to kind of decouple the resources from the application container. We can avoid including the model weights or system prompts in these giant, all these giant resources from the actual CVM, such that we can kind of elegantly put these into its own layer of transparency ledgers or something like that. So we leverage transparency proofs, and we kind of use those as the way to kind of decompose the attestation, such that we can kind of verify that these are part of some other ledger. I have a better visualization here, but say we have a model. We will generate a hash from that. We'll publish it to the transparency log here, and then we'll get a hash of that transparency log. Pretty standard fare. Afterwards, we'll take that same untrusted model and we'll put it into and some sort of binary transparency proof, and then we will kind of try and use this binary transparency loader in the CVM to kind of load it into the CVM. Have that binary transparency loader generate the hash of the model, and then we do a couple of simple checks here. We'll check that the hashes match what's provided in the binary transparency proof, and then also just make sure that that's signed by Cloudflare or whatever our transparency ledger is. It doesn't have to be Cloudflare, but that's what we use at Meta. Once we verify that these two things are valid, we will then trust the model and then present it inside of our attestation reports. Next up, I'm going to have Henry talk about some of the operation work.
Right, so bringing up the private processing stack was a lot of work. But what's also a lot of work is maintaining it and evolving it over time, as we have to uphold the privacy, security, and transparency guarantees. So in this section, we'll talk about some of the operational work we do to make this happen, with a focus on managing vulnerabilities. So our privacy and security guarantees rely on not only the TEE hardware, but also the integrity of the software that's being deployed. So we must take care to minimize the risk of bad code or malicious code being pushed to production. However, Meta's software supply chain environment makes this a little difficult for the following reasons. We have a large engineering organization. I can't say the numbers, but it's getting less with layoffs. We have a model repo with broad access. So this means that hundreds of teams share the same code base. Anyone can generally push code as long as it's being code reviewed. We have general TCB bloat. TCB bloat here means the amount of code that is measured and attested. Now, while we cannot guarantee that no bad code will ever be landed, we can enforce controls to make it difficult for a single malicious insider to push code to production on their own. So we have several enforcements and internal controls. For example, artifacts must be built by a trusted builder. It must be built from a landed or accepted source revision. Deployments also require collaboration between multiple teams and multiple individuals. We also heavily use AI throughout the deployment process for code reviews and as well as to continuously audit the code base for potential vulnerabilities. Furthermore, every stage of the deployment generates internal audit trails. So that acts as a deterrent for malicious behavior as well. And finally, the load-bearing component is binary transparency, since any artifacts we deploy to production have to be published to a transparency log. Now, about the dependency load. So at Meta, our model repo incorporates hundreds of third-party dependencies. And as we see software supply chain attacks become more and more sophisticated, this is becoming a real and growing problem. So to address this, and this risk is actually further exacerbated by the fact that products typically prioritize more feature support over just minimizing the TCB. And as we know, TCB generally scales with vulnerability risk. So to address this, we have vulnerability management infrastructure. It ingests CVE data from multiple sources, it scans our code and binaries for potential vulnerabilities. So we use these signals to gate pushes to production, as well as to raise alerts about possible vulnerabilities in active deployments. Now, even with all these controls, right, there is still the chance that these vulnerabilities inevitably reach production. Therefore, we need a mechanism to mitigate these incidents, and it has to happen fast. So this brings us to our next topic, revocation. Revocation just means invalidating particular artifacts. So imagine a client connecting to a server, but rejecting it because for some reason it's revoked. So we have revocation with expiration time and explicit revocation with a revocation list. So for the expiration time, binaries are like milk. They go bad over time as they accumulate CVEs. So we enforce expiration for all of the artifacts we deploy to prod. What happens is the WhatsApp client, when it tries to connect to a TEE server, let's say it's running a CVM image that's more than 90 days old, it will reject that connection. However, expiration time on its own is insufficient. Imagine if we have a server-side vulnerability, we hotfix it, we fully deploy it, or we think we do. Because it's possible for some vulnerable instance of the server to be running within our infrastructure because Meta is untrusted, and it can pass attestation up until it expires. So this could be in the order of up to 90 days. And during this time, traffic could be routed to this one vulnerable server, and data could potentially be exploited. So to mitigate the risk of these long-living artifacts and the fact that it takes us actually 90 days to roll out changes to the mobile client, we have the concept of revocation lists, which is simply metadata containing digests that correspond to revoked artifacts. So revocation lists are also fresh. We have freshness enforcements. They expire after 24 hours, and we continuously refresh them. So this means that after we revoke an instance of an artifact, clients must see it within 24 hours, otherwise their attestation verification will fail due to these freshness errors. Lastly, the revocation list is also a transparent artifact, which means its digest is published through the transparency log, and the content itself is actually available to be downloaded by the external researchers. Therefore, Meta's revocation operations are transparent. And what happens is researchers can verify that we are not doing any malicious operations. For example, if we unrevoke a binary before it expires. So revocation only invalidates the transparent artifacts, which are the CVM and application software packages. But what about vulnerabilities or hotfixing the AMD firmware? This is tricky because currently the TCB values or the firmware versions are hard-coded into the mobile clients. And for us mobile clients, we don't control their updates. It takes up to 90 days for these rollouts to happen. Therefore, we rely on another mechanism, self-attestation. So this works where the CVM boots up, it measures the firmware versions, compares it against a hard-coded set of expectations, and if the verification fails, then we refuse to boot. So to tie this all together, let's talk about a real-life incident where we had to use these exact revocation hotfixing mechanisms. So let's say we have to update the AMD firmware across our fleet. We apply the patch code and we roll out to all the hosts. Next, we have to rebuild the CVM images with new expectations for the new firmware versions. Because if we don't, then it's still possible for these vulnerable servers running the vulnerable stack to be deployed. So then we add these vulnerable CVM digests to the revocation list. The revocation lists are distributed very quickly to the clients, and clients are immediately able to reject connections to any stale CVM instance running on the stale firmware. So the important thing is that we're able to move fast, and the fact that these operations are transparent and can be audited. Next, Liz will talk to us about the bug bounty program and the future plans for the platform.
All right, good afternoon. The last part, we're going to talk a little bit for non-technical part. And let me quickly introduce our bug bounty program. So Meta has amazing bug bounty program cover our major products. And for the public program, it's open to any external security researchers. If you have any interest, just go to our website to have a look. And as part of our commitment to verifiable transparency, we also provide a bug bounty program for researchers to audit the WhatsApp private processing stack. So we want to be as transparent as possible and also open source as many components of private processing stack as we can. And for the starter, we have already open sourced the Attestation verification library, which run on both mobile client and also within the TE workloads. As a matter of fact, we just open sourced Attestation verifier library, and it's available and open from today. So please go to our GitHub and check it out. And the link is on this this slide. So for one thing I need to mention here is for the WhatsApp private processing bug program, it's a private program, so it's by invitation only. In the future, we plan to open source more components and also continuous improving our research environments by modernizing our documentation and tooling. And on this slide, what you can see is a UI for our private processing bug bounty program. So the researcher who enrolled in the bug bounty program can just go there, download transparent artifacts whose digest has already been published into the transparent log. Researchers can run or decompile the binaries to verify privacy preserving and also inspect the security of our systems. Okay, all right. So in the past couple minutes, we did recap what happened before and what we're doing right now. So what is next for Meta private processing? In summary, we are right now turning Meta private processing as a strategic platform, which is measured, attested, transparent, and introspectable. Right now, we already have the 4 capabilities in place, but we want to continue enhancing all those 4 capabilities. And what's more, what I want to share here is in the first half of this year, we actually did internal customer interviews. So we have collected lots of use cases, lots of new requirements. And as just we mentioned in the very beginning, we just released Incognito Chat in May, this first half of the year. We're actually also working on more new use cases. So we're definitely going to have a more exciting news to share in the second half of the year. As a matter of fact, in the next year's conferences, we're going to have much, much more exciting stories that we can share with you all next year's conference. All right, so as we just mentioned, as a platform, we actually have 2 focuses. One focus definitely to strengthen on our platform foundation, which means that we need to improve our hardware security, explore more hardware options, and of course, we're going to expand CVM features. So for example, Mewtwo RA-TLS, we support client-server Mewtwo attestation, and we also going to implement CVM trusted time to prevent time-based attacks. And we're going to implement new virtual machine managers, cloud hypervisor, provide less attack service than QEMU. In summary, we want to make the platform more secure, more reliable, and more scalable. So that's our focus. And of course, as a platform service provider, we want to improve our internal developer experiences. We're targeting provide frictionless onboarding experiences to our developers, and we're proactively engaged with our customers. So we've been very proactively working with them to seek more feedbacks, identify new use cases, identify new requirement, where we can potentially use confidential computing to solve the technical challenges, and especially where that we can actually use the confidential computing as our new business revenue generator. So that's our 2 focuses for Meta private computing as a whole. With that said, that covers all our sharing today. And I want to call for all our Meta team members to raise your hand so that please, team members from Meta, raise your hand. And if you have any questions, and talk to us. Thank you so much. And again, we're open for any questions and discussions. Thank you.